There, everyone, and thank you for coming. And we're going to talk about DuckDB, which is an embedded relational database for Python and other environments. And we're going to try and cover 4 things today. We'll see how we do. First thing is just a sort of big overview of what data science looks like these days. So a lot of what DuckDB gets used for is in data processing pipelines. Now, I talk to you possibly in too much detail about what DuckDB is and how it works and what the performance do with it. I'm going to show how it integrates somewhat nicely with Python. And then, because you've actually got me physically here, I thought I'd take a little time to talk about some of the work I do, which actually connects very well with some of the impedance mismatches you get sometimes between people who are used to using data frames and people, and the SQL world. So a little bit about me. I actually got started off in signal processing back in like the 1980s and 1990s, first in analog and then doing some speech synthesis stuff. And this then morphed into doing one of the first streaming clients for music at real networks, and eventually working on some video streaming with a friend of mine. Then I made this strange leap over to software, the visualization pioneer. And one of the things I did there was I started learning about high-performance databases, because we found that talking to regular databases. So we worked on this thing called the Tableau data engine, which was a columnar database, which was a big thing back then, about 15 years ago. I even got to work a bit on this compilation, taking SQL and turning it into LLVM, or assembly language, basically, which is a real bear. That this is a system that Tableau bought called Hyper from some German academics. And then I retired just before the pandemic and got very bored and started hacking on DuckDB, which I'd run into them at a conference. And then they asked me to, if I wanted to sort of work on it a fair amount of the time, and that's what I've been doing actually since then. So first of all, talking about data science. This is a big thing in the modern world, and the data processing, the data crunching is a very important part of these pipelines. So what do these pipelines look like? Well, they tend to be this loop that you go through. The cycle of data analytics is what my friend Jock at Tableau used to call it. And there's other people who've done some very academic things. You ask a question, you get the data that you think might have something to do with the question. You then explore that data. You then model it once you've decided it's the right thing. And then you visualize it so that you can understand it, because using visualization is one of the best ways to get high bandwidth into your brain, if you will. So what does this look like in practice most of the time? You've got all of these different tools and bits and pieces that you're using. You have data frames, you have databases, you have JSON, you have data frames, you have PyTorch, TensorFlow, Plotly to produce the results and all the stuff. So there's all these different tools, and what do you glue them together with? You glue them together with Python. And this is where the whole, big data in Python thing came from. You just have all of these tools that have been written to scale up and do all of this work. And there's a lot of stuff to do. You have multiple file formats, you have a huge number of ecosystem tools, and you have so much data that you're processing that you want it to be executed very efficiently. You may not have enough RAM in order to do all the computation. You want to make sure things get done in an intelligent order so that things get done as fast as possible. Because if you are working with data and you get into a flow state, if it takes too long, you're suddenly thinking about what's for dinner or something. And that's not very, that makes you less productive. And the last thing here is that all of these tools, they've come up with sort of standardized APIs and ways of thinking about things. But do you really need to worry about big data? The argument gets made that you actually don't. right? So there's this famous result from Google saying that if they went out and looked at what BigQuery was processing from internal work, and they found that 90% of all their analytic workloads were less than 1 terabyte of data. Well, guess what? That fits on this machine right here. And I've even seen work from MIT, which suggests that an awful lot of data sets are actually under 1 gigabyte. So you may not have a lot of data, but maybe you want to do something complex with it. If you can get a system that will do that efficiently on your laptop, then you can save all kinds of costs. You don't have to pay to transfer data out of an S3 bucket or something. You don't need to rent new hardware. You've already got it right in front of you. And this is, in fact, what DuckDB can do. So this is I forget exactly what the query is, something Mark did a little while ago. And he compared running some substantial but highly parallelizable query on DuckDB and on a Spark cluster. And he had to get up to something like 32 nodes in the cluster before it was competitive with his laptop. So this is the sweet spot that DuckDB is aiming for. So what is DuckDB? Well, it's an open source, embedded, vectorized analytic database engine. And we're going to go into all of that. But the first thing people ask is, why DuckDB? Well, ducks are wonderful creatures, very flexible. They can walk, they can fly, they can swim, they can float on top of the data lake. Oh, well, not quite. But that's actually not where the name came from. Hannes, pictures here, is one of the founders, lives on a boat, which you can see behind him. And he decided he wanted a pet, and he figured a cat would drown, so he adopted this duck called Wilbur. It's in there. And this picture is not done by a friend. This was actually in the Manchester Guardian when they went around Europe looking for people with exotic pets. Eventually, Wilbur figured out he was a pet, and the great duck pondens. But his legacy lives on. So what exactly is DuckDB? I mean, I think everyone here is familiar to some extent with databases, relational databases. Okay, well, we got this sort of graph we use here to describe the different, at a large scale, architectures that people use for databases. Along the x-axis, we've got the two main classifications, which are transactional and analytic. A transactional database is what you use when you're doing work in, say, a shopping cart. You have lots of little changes that get made to entire rows. And in the client-server world, we have Postgres. It's a very common open source one. These are all open source tools to avoid anybody's lawyers getting upset. And there's also SQLite, which is an in-process transactional database. Over on the analytics side, these are databases that are designed to deal with processing large amounts of data, but a subset of it, maybe just a few columns, doing aggregations, doing moving averages, sorting it, large amounts of data. And one example of that that's open source, although I just saw a news story today that they're starting to non-open source some of their better features, is ClickHouse. Into this? Well, we are an in-process system that is designed for analytic workloads. So you don't have to set up a server, on the one hand, like you would for Postgres or ClickHouse, and you don't have to deal with single row at a time operation like SQLite. So we are optimized for this particular work case. And sometimes I just must say that people get a bit, competitive between these various tools. We love SQLite. We took a lot of inspiration from them, but they're designed for a different workload that they are, in fact, better than. Also, we love the fact that they're so well tested they can be used in airplanes. We're still aspiring to that. So, where did it come from? Well, it came out of the same institute as Python, actually, as CWI. And the researchers there were talking to some people doing some genetic analysis and found that they were not using SQL because it was too hard to set up. They had all these text files and they were just crunching them using various Python. So they decided to set out and build the system that these people actually needed. So here are all the design goals. They wanted simple installation, no external dependencies even. You just want to be able to install it and get going right away. No server to set up, nothing to worry about, no ports to manage and open up and all the rest of it. No configuration necessary. We should handle all of that ourselves. And SQL is a very established language, but it's sometimes a bit opaque. And so we've also been doing a bit of stuff to make SQL easier to use. You can put extra commas in. You can put the from clause first. So lots of little stuff like that. Group by all. I'm not going to go into that too much. But this is one of the So what is the installation experience? Install DuckDB. That's it. Just put it in and you just start using it inside of Python. And so there's an example. You import it, and then you can start querying for life, the universe, and everything, which is all you really wanted to get out of work anyway. And unless you think that I'm trying to sell you something that's not widely used or supported, this is last week's download statistics. We're up to about 1.5 million downloads a month at this point. So you're in good company. There's a very large community out there of people using this tool. And we are all online and ready to help you out. So analytic means fast. Our big focus is not simply on being integrated, but being fast, because if you just wanted to do a bunch of relational operations, Pandas already does that. But we are focused on using state-of-the-art database construction techniques that the community has been working on for a very long time, almost as long as I've been alive, and I'm not the youngest person in the room. So we've been using all of these techniques that have been developed, especially in the last 15 years, to make the execution a lot faster. This includes things like columnar layout, a vectorized execution engine. We parallelize computations, unlike a lot of these native Python tools, which are kind of stuck being single-threaded. We can melt your machine down if we really want to. We do query optimization. What order is the most intelligent thing to do thing in? This is a big topic in the database research world. And the last thing we've been working on a lot recently is making sure we don't run out of memory. Okay, I mean, if you've ever tried to do any processing of something large in Python, you may run out of memory. We can page a lot of this stuff to disk, so we're actually using your SSD drive, your hard drive, instead of just being stuck with RAM. So I keep throwing this term vectorized columnar work around. So let's talk about what this actually means. SQLite uses a very traditional system going back to the 1970s called tuple-at-a-time processing. So you just do one row at a time. It's all very interpreted. You don't use a lot of RAM for this, but it's very slow because everything you do requires a lot of code to get it to run. And it's also not very well tuned for modern hardware. Pandas uses something called column-at-a-time processing, and there are, in fact, some academic databases like Monet that do this as well. So this works a lot better because you only need to read the columns you're actually going to use. The processors can do prefetching, but you have to be able to process things in a lot of RAM. And if you notice, if you've got a lot of data, this modern CPUs have these memory caches, and the larger the data that you're processing, eventually it gets kicked out of the cache, and then you have to read it back in again, and that's very slow. So what we take as our approach is called vector-at-a-time processing. So we break the data down into 2K chunks of rows, and then we push them as far as we can. And this is a sweet spot for modern hardware. It doesn't use a lot of RAM. You can get fast data accessing because you're still prefetching data from the caches, but everything stays mostly in the caches, and so you can get very good performance. You're not sitting there waiting for memory. Another thing we do is end-to-end query optimization. So we rewrite expressions, we reorder joins, we flatten subqueries so that you don't have to run the query every time, and we do something called filter pushdown. So that's the example here. That if you write out a filter and an aggregate, DuckDB will actually push things down close to the data so you don't have to read everything. And this sort of stuff is automatic with our query optimizer, and generally most of those techniques, you can do them in pandas, but you have to think about it. But by using SQL, you just describe what it is you want to have happen, and we handle the rest. We can also do automatic parallelism. All of the major operations, relational operations, have been parallelized. So scanning, computing expressions, if you've got just some arithmetic you're doing, we will do it completely in parallel, one block on each core. We have parallelized our joins, our aggregations. I'm doing the windowing. That's and is highly parallel as well. And parallelization is actually somewhat difficult. You have to make certain that you have your load balanced and that things are scheduled properly. Load balancing means you want to keep all of the threads busy. And scheduling means that you want to make it so that you're not trying to do things that depend upon each other. And lastly, beyond memory computation, we use a lot of we all have various science fiction sources of inspiration, and one of them, Galaxy Quest. So we support processing larger than RAM data, and we're very good at doing gracefully degrading as we start to use the disk. Our goal is to never crash until we maybe run out of disk space, which hopefully won't, and always execute. And so we've been working on a lot of these operators recently. And this graph here just shows that as you take this query down from 10 gigabytes, we can actually say how much memory you get to use. You see it only gets about twice as slow, even when we cut the memory down by a factor of 10. So, some benchmarks. Benchmarks aren't great. You should check it for your workload, but this is from last May. These things change every week, but this is a benchmark we did not write, and we're basically at the top of the queues for these compared to these various tools. So that's the engine, and that was. Let's get back to Python, because as I mentioned a little earlier, DuckDB was originally invented to work inside of Python, because there were some people in the research institute who were doing all their work in Python, but didn't have anything to crunch their data for them. So we're very tightly integrated in the Python environment. One of the things we can do is read your data frames directly. You can query them. And we don't copy the data. We just start processing it. We just create pointers into the memory and then use that to run through our SQL engine. But we also can scan these data frames in parallel. And we're very well integrated with a number of sort of common formats, and we have an API for if you come up with another one, we can add to it. So we've got CSV, Parquet, I'm doing a lot of work with Arrow. We also can read SQLite files directly, so you can keep doing your SQLite work, but we can then do analytics work on it much faster than SQLite can. So you can get the best of both worlds. We can also read Postgres data files, but not while the system is running. But we can do analytic workloads on native Postgres data. And I've already got a little ahead of myself. So there's an example of what it looks like to to work directly with a data frame. We can have pandas read a CSV into a data frame, and then we can go and filter it just using standard APIs. And we have the same kind of composable interfaces like a lot of these other libraries. But the difference is that if you stack a bunch of these operations together, like filter and aggregate and sort and all the rest of it, we'll actually take it. That's not a pipeline. That's a description of a pipeline. And when you ask for the data, we then take that description and optimize it so that it runs really fast. And there's a whole bunch of tools out there, and we play very nicely with if you want to see like a Jupy SQL, I have a do later. I don't think I'll have time. So this is a comparison of all the various ways you could do data crunching inside of Python. And we have, in fact, these sorts of slides are always like, well, we're better than everybody else. But actually, we've been learning from these people. We learned what it is that is a friction point for users like you. And we come in and we go and try and make it better. So last thing I'd like to talk about is these ordered operator thing I work on. And some of this is a little unusual for and specific to DuckDB as opposed to some databases. There's this thing we often run into that when you're working with data frames, there's this natural ordering to it, your index. So you expect to be able to write loops and things that maintain the order. But the relational model invented by Codd in the 1970s, the data is viewed as a set. So there's no inherent ordering. So we're constantly trying to bridge this impedance mismatch, if you will, between these two ways of looking at data. The foundation of this is our sorting code. And our sort, I believe that, name there, but one of our members is a PhD student, Lawrence, and he actually has the fastest sort in the world, and it's in our code. It's mental, right? In order to do all of these ordered processing types. And this isn't just used in order by, we've broken it out so we can use it everywhere in all these different types of ordering things. And I'm one of the big clients of it. I'm going to go through some. But you can see from this graph that we're a lot faster than a lot of these other systems. First place we used it was just doing when you have an order by clause and a select statement in SQL, so that our sort is full. We can page it to disk if we need to, and the limit clause will not sort things it doesn't need to. So you can have an offset and a limit, and it'll be fairly clever about it. My big thing is windowing. So if you ever wanted to know how to deal with ordering and adjacent row computations in SQL, this is what it is. It's called the clause. You do an over clause. You say, I want to break the data up into these independent chunks, partitions, and I want to sort each one. All of this stuff has been fully parallelized and vector, and it also pages out to disk. So we can do windowing on stuff that's larger than memory. We also have some very state-of-the-art stuff around how you do aggregation. We can parallelize the computation of moving averages, for example, using a technique called segment trees. We've also got some of my work in there on so you can actually do a moving interquartile rate operators. There are better ways of doing that, my friend. Well, most of the time when database people talk about joins, they talk about equijoins. This equals this. But when you're dealing with messy data, what are called state tables, and you have a start and an end, and you want to join two things on an overlap. And so we have a support for what are called range joins. And this example over on the left is taken from Battlestar Galactica. The difference between when someone is on patrol and when a battle starts. How do you compute combat and the table shows the intersection join produced by it. We have two different inequality joins optimized for one or two or more quality conditions. But just another way we're trying to get ordered processing system for making everyone's life easier. One of the more recent ones we've done is something called an as-of join. And this is when you have timestamps that are a bit fuzzy, or you have some data some events that happened at particular points in time, like prices for stock trades, and you want to know what was something worth at that particular time. Well, you don't know the exact time when the trade happened, so you want to be able to find the most recent one before the time you're looking at. We have put this in as of the previous, continuing. And this one is this thing called positional joins. And this is not something you find very often in SQL. And the problem is that if you're used to just dealing with arrays, you want to be able to go down them like this. SQL doesn't let you do that because it doesn't have much of a notion of order. So we have a thing called positional joins. So if you have, say, 2 data frames or 2 Parquet files where the rows line up, but there are different files, there are different frames, you can actually stick them together properly in DuckDB and then proceed on with further analysis. It's only serial right now, but parallelizing it is another thing on my to-do list. And with that, we come to the end. So things I want you to remember: we are fast, we are easy to use, we are very Python native, and we can make your laptop do more than it can normally do in RAM. All right. Except, Zal, we'll have some time. Yep. This is the first time I've given a talk in Meat Space since before the pandemic, so shake. Oh, yes, sorry.
Yeah, they don't care like Wesley, Wesley or the.
That's a very good. I think we can. Yes. Well, I was about to. Yeah. So the question, if there's a thing about whether you can, how much parallelization you do for a single query, or whether you can parallelize running multiple queries at a time. Generally speaking, can do both. Mostly we measure just doing one at a time and really maxing it out. But one of the issues that you have to be careful about is that you can't have multiple connections to the same writable database. So the only way you could really do that is to have multiple threading inside of Python, which is not impossible. So you can actually run multiple processes as long as they're doing read-only queries. But for the most part, we're focused right now on just running single queries very efficiently. I mean, what you're asking about is something that tends to be more of what a server would do. So, but yeah, I mean, if you want to try that and have issues with it, please let us know.
It's nothing very word, but you will. You're gonna try and get it done. A little bit like.
Sorry. Oh, persistent memory. This is something that the database community has been writing papers about for a long time. But the general consensus at the moment is that it's not very cost effective, and there's things you can do with that that are just as good. Yeah. Students right now who have been writing papers and degrees on this, and so they come to conferences and present this stuff, and we're all going, yep. So. Usually there's good APIs for it. I'm sorry, I don't know if he's asking about technology called persistent memory, which is something people are. It's a type of memory where if you turn the power off, it still remembers what's going on. It's lower and more expensive than regular memory, but hopefully cheaper than disk space. But the community has been finding that does. So,
Cool. Thank you very much.
You're welcome.